Hi there, welcome back. In the last session, we defined the problem statement. We divided a problem statement into three logical stages. Now we are going to talk about each of the stage in detail. In this session, we are going to talk about the ingest phase of our problem statement. So now let's discuss about the ingest phase of this system design problem. So before we jump into designing any system design, we need to first ask some questions. This is very crucial. Even if you are going for a system design interview, the first thing you ask is, after looking at the problem statement, is what questions I need to ask is what very key thing, because the questions you ask will determine how you are going to design your system next. So to start with, first we need to understand what protocols are the sensors are using. Is it something like MQTT, or it is some kind of HTTP, or any custom protocol? The reason we need to ask this question is this will tell us how we connect the ingestion system to the IoT sensors. Next, we need to ask how frequently do these sensors are sending data. Are they talking about messages coming every second or every millisecond or every few hours a day, or maybe sometimes it could be that I send a message only when it crosses a certain threshold. When temperature goes above this particular Fahrenheit only, I will send the data, right? Is that what the case? Because the reason we should ask is this will drive our questions on throughput or maybe our scaling, right? Next, we need to ask the question of how many devices are in play. A few hundred devices might be might work with a something like a basic setup, but if you're having thousands of sensors sending transmitting data every second, that requires a little bit more planning, on how do we handle the connections, the message durability, what happens network goes down. So we need to handle a lot of cases. Next, we need to think about the data, right? What data looks like. Are we talking about something like a JSON format or a simple text format, or it is maybe it could be some simple text or JSON or chemical arrow. So we need to see like the reason this is important is this is how we need to understand how we are going to pass the data, how we are going to enforce a schema down the line, because for all these things we should understand the data structure, data format. Then we have to ask how time sensitive is the data. So for example, is the latency critical? For example, if I get a data a few seconds delay, is it acceptable? Instead of getting the at the time t1, I have to get the data time t3, whether is it acceptable, or can I take the data from time t1 the data got generated, but by the time I received it has become time t3 received it. Can I still take this data and process it? Or maybe the data at time t2 arrived before time t1. So do I need to process the data from time t1 first and then only I can process time t2, or maybe I can discard the data at the time t1 and start processing data at time t2, right? So these things will determine how you design your real-time or near real-time pipelines. Next one is that reliability is another key factor. Can we afford to lose some messages, or do we need to guarantee delivery with retries and buffering? What happens if I lose a data from few sensors at a particular interval of time? Because it's a big system, there could be network delays, there could be some transmission delays. You might lose some data from a sensor. So what happens if I lose the data? Can I afford to lose some data? Just I can ignore that. Okay, yeah, there was some network error. I couldn't process the data at that time. Or we also need to ask, should we store the raw data right at the ingestion point? So the reason is sometimes we overlook, because a lot of times if you want to go back and see like what went wrong, right? Maybe you have taken the data, you did some parsing, you determined that the system is going down, but that is not the case. If you want to go back and see like what went wrong, you always need a raw data which is required for your audit purpose. And finally, the most important thing, right? The security. Are our messages encrypted in transit? Are devices authenticated before they send the data? So all these questions help us to understand not just the tools we use, but how do we configure them to meet the actual, the not only the business or business needs, but also the technical or non-functional requirements. So once we answer these, then we can move forward with the designing our ingestion architecture. And if you see in our case, these questions are answered. Like we know that we are having a 2 million records coming per day, and we are having thousands of IoT devices, and then we require to process them in near real time and then do the ML inference in near real time. Once we have asked the right questions, we can now define what we are actually trying to achieve in this stage. So let me read out what is the end goal of this stage, right? We need to reliably collect data from hundreds, maybe thousands of IoT sensors that are sending messages every few seconds. The data needs to be streamed into central system that is scalable, fault tolerant, and durable. Something like Kafka or Kinesis, where it can be consumed by downstream processors. So our pipeline must make sure no messages are lost, maintain the order of messages per device, and be able to handle any bursty or high volume traffic without without choking the system. And another important goal of this stage is that the system needs to do all with the minimal latency. I need to able to detect if anything is going wrong in any of my systems in my industrial system. I should be able to detect quickly, right? What it means is that I need to invoke the ML model. The inference has to happen quickly. So to summarize this phase, we are setting the foundation for entire pipeline actually. If we get this wrong, lot of things, everything will go wrong down the line. So if you are not able to ingest reliably, your ML inference will go wrong, your data storage will go wrong. So entire ML pipeline will depend on how reliably, in how accurately you can capture the data from the sensors in this stage. So now let's start with multiple design options. What we could for this problem statement, I'm assuming that we'll use AWS as a cloud platform. We could use any platform like GCP or Azure, but just to keep it simple, because to focus mainly on the key essential aspects of design, I'm assuming that we'll use AWS. So within AWS, you are having two options. One is AWS MSK and then AWS Kinesis. So what is MSK? This is AWS fully managed version of Kafka. What it means is that you can get the power of Kafka without having to worry about setting about the infrastructure, right? You don't have to really worry about how to manage a broker or zookeeper or cluster. Everything is handled by the AWS. And if you're already on the AWS, right, it directly works with integrate with your, you can be in your VPCs. You can use your IAM roles, you can use your TLS encryption. For monitoring, you can use CloudWatch, right? So if you're already having AWS stack, this makes your life easier because it is already integrated. So only one consideration is that it runs inside your VPC. So your producer setup, like whether you are using some IoT gateway or some connector, need to be in the VPC also. So this MSK is ideal if you want to have a Kafka compatibility with a reduced operational overhead. And also most important thing is that it helps you with it is very tightly connected with your AWS ecosystem, right? So in that case, the AWS MSK is one option. So we'll explore another options again, like about the Kinesis. So what are the Kinesis? And within MSK also we're having MSK managed, MSK serverless. Let's see both of them. What is the difference? So AWS offers MSK in two flavors. One is provision and another is serverless. So with the provision, the advantage is you get full control. You choose a number of brokers, their size, and how your topics and partitions are distributed. This is a great for high volume mission critical workloads where you want to have more control over how you want to configure. And other important thing is that you know that what is the what is the predictable performance, or maybe the number of messages you get per second or per day. But with MSK serverless, which is, AWS handles all the scaling for you. So you don't need to provision brokers, or you don't have to tune your partitions or worry about the cluster size. It's Kafka under the hood, but the experience you get is a serverless experience. So when this is serverless is ideal for you, when your traffic is spiky or unpredictable, or when you want to have the power of Kafka without any operational burden. So the trade-off is that serverless has got a throughput limit, something like, maybe this could be changing no every, because when I'm recording this video, maybe it could be 200 mbps write and 400 mbps per read, but this could change. Maybe the AWS will keep updating this throughput limits every now and then. But for many real-time IoT use cases, whatever the throughput what the serverless offers, like which is about 200 mbps per write and 400 mbps per read, should be more than enough. So depending upon your workload type, whether you are having a predictable workload or you want to have a spiky or bursty workloads, you can choose between provisioned and serverless cluster under the same MSK umbrella. So the key thing is that you're still using Kafka, but it's all about whether you want to manage a lot of the operational overhead, or maybe sometimes you want a quick POC and you want to test something, you want to make system up and running. So you don't have to really spend a lot of time on deciding like what is my the partitions I want to use, tuning everything. I just want to get quickly. In that case, serverless actually offers the best option. The second AWS native option for handling all this streaming data is AWS Kinesis. This is also one of my favorite, because one reason I like is it is very simple and easy and intuitive to handle. So this is again a fully serverless service, which means you don't have to worry about the provisioning, scaling, or any other infrastructure management for you. So you just push your sensor data and it scales automatically based on the demand. It is also optimized for a real-time event ingestions, offering very low latency delivery and built-in integration with either Lambda or S3 or SageMaker, or even KDA, which is Kinesis Data Analytics, or maybe Firehose. Or maybe if you want to just don't have too much of processing required, you just want to ingest the data, you can also use Firehose, and you can send to multiple destinations like S3 or Elasticsearch or maybe DynamoDB, like you're having multiple destinations. So the Kinesis also makes it ideal for event-driven pipelines where you need have minimal delay, and the most important thing is if you're already in the AWS ecosystem and you want to easily integrate your ingestion pipeline with your existing systems in AWS ecosystem, Kinesis actually is the best choice. Okay, but the difference is that a lot of times, depending upon your scale, if you are looking for a millions of ingestions per second, and then you want to have, and at the same time you want to have more Kafka type of compatibility, because you assume that you are already wrote a lot of your consumers in Kafka, or your team is already knows about the Kafka, then obviously MSK makes more sense than the Kinesis. But the Kinesis gives you a powerful, elastic, and operationally simple way to ingest high frequency IoT data. And there are some features in Kinesis, something like enhanced fan out. Okay, what it means is that this allows multiple consumers to read from the same stream in parallel without slowing each other down. So which is very essential if you're building a complex pipeline. You might have something like some logic like a branching, or logic, or some analytics. So in summary, if you're looking for a simple tight AWS integration and an event driven trigger or pipeline, then Kinesis is an excellent fit, especially when you don't have to, your team is comfortable working with either Kafka or Kinesis, the consumers, end of the day, then Kinesis is your best option. Next, let's see based on our problem statement whether we choose Kafka or Kinesis. Like now, assume that. So for this problem statement, I'm choosing Kafka. Like let's see what is the justification. Even if you go for any system design interview, you need to justify why you choose an option. You can lay out the options, okay, and then you have to give a justification like why I choose this option. So why we choose MSK instead of Kinesis here? So number one is that the scale and reliability. We are handling over 2 million messages per day across hundreds of sensors. So we have chosen Kafka especially as our ingestion layer, especially for this reason. The reason being, Kafka is a proven high throughput streaming platform that gives us the kind of ordering guarantee we require and the kind of durability we require and the kind of visibility we need, for the mission critical IoT pipelines. Since our goal is we need something to build a long running system that may evolve over a time, and we want the platform that support a fine-tuned control over topics or partitions or retentions, something Kafka really does a good job of it. So the main advantage of using MSK is that we offload all the operational burden of managing the brokers, the cluster. Still, we have a retaining the full control of the Kafka system, and we are also getting the advantages the scale the Kafka offers. And more importantly, we have a flexibility. So because if we expect a what I something like consistent volume, so we can use a provisioned MSK. But if I'm having a bursty traffic, I can go for MSK serverless without changing any, mostly not making too much changes to our client code. So the the bottom line is that the Kafka ecosystem makes also easy to plug into analytics or maybe invoking ML model. So which is aligns well with what is our goal of the system, that is uh, to able to invoke ML model in near real time and process it at the scale. So that's one of the reason we have chosen Kafka as our recommended choice for the ingestion platform. So now that we have selected Kafka via Amazon MSK, let's look at some of the key design considerations in Kafka. So in the table below, I listed some of the key design considerations. The number one is the topic strategy. This tells about how many topics you want to create. Again, this is driven by your use case. If you want to handle a separate processing for each sensor, like temperature different or maybe the vibration, humidity different sensor, obviously create a different topics for each. But if you are not worried about, but you want to look at holistically all the parameters and then make a decision, one topic should be good enough for you. And again, it's also depending upon number of messages you are getting, all the load will determine the number of topics. Next one is a partitioning. So this is one of the most important design elements in Kafka. So if you think your topic is like a highway, partitions are the lanes in that highway. So more lanes means you have a more traffic can flow in parallel. So but let's understand how this partitioning works. So in this example, if you can see that it is basically creating a hash out of one of the key element, in this case device ID, and then assigning that message to that particular partitioning. Now the hash of 1278 is say 0, then all the messages from that device goes to partition 0. So anytime you are getting a messages from 12788, that they will always go to the partition 0. That way you can ensure that one partition is having only messages from this. This helps in equally distributing the messages across the partitions and also to have a dedicated consumers to process the messages from a particular sensor. The next important design considered replication pattern is this is all about fault tolerance. So each partition is replicated across multiple Kafka brokers, usually 3. So basically what it means is that when we have a replication factor of 3, this is kind of something like a standard which will work in most of the use cases. Next, retention policies. This will tell you how long Kafka should keep the data before deleting it. So even if something like if you're having something 3 to 7 days, that gives you a good buffer range to reprocess if something goes in the fails in the downstream systems. Next is the schema management, which is critical. Over time, the devices might start sending new fields, and without a schema enforcement, that can break downstream system which are processing your messages might break. So we can use something like glue schema registry, to enforce this structure and also the versioning. So on the security front, we can use something like a TLS encryption for all in-transit data, and also Kafka supports access control using IAM. And also, we can also deploy all the brokers in a private subnet so that they are not exposed publicly. So, and then for monitoring, we can monitor the consumer lag, which tells us if downstream process is failing, behind. We can also watch, the broker CPU or something like disk usage or maybe a replication status, all using the CloudWatch. And we can also consider some tools like Prometheus or Grafana, if you want more detail or a granular level of insights into various metrics, how the way the Kafka is processing. So what is most important thing is that these are the key critical building blocks for the Kafka pipeline, so that we can handle the ML inference in real time, and also we can scale the messages, and also we are fault tolerant. So now let's see how do we choose a number of partitions. I just thrown some number like 24 to 48. It could just I just thrown this number to help you to walk you through the how to do that, right? So if you see, right, first we take our problem statement says that we expect about 2 million IoT messages per day. So which comes to around, you could say around 1 gigabyte per day. Okay. So this might not sound like a lot, but because these measures comes in continuously, and sometimes it could come in potential bursts. For example, if you're having more production happening certain time of the day, you might get more burst traffic. So that our system need to handle the spike in traffic. So assuming that we are planned for about 5 megabytes per second of peak throughput, this gives us a good headroom to scale even if our average is lower. Now, a single Kafka partition can safely handle about 1 to 2 megabytes per second. So if we divide this 5 megabytes per second, say by 1 megabyte per second per partition, that gives us about a base of around 5 partitions. But we are not stopping here, right? We are also designing something for the flexibility. So if we choose something like a 20 or 24 or maybe even 40, we give ourselves ability to scale out consumers workload like ML model inference or stream processing, dashboard, and more across multiple nodes or threads. So even if you future you are expanding this to a lot of other, say instead of one production line you want to multiple production lines, and then you are getting more sensors, say instead of 2 million it might go to 10 million messages per day. This will give you enough headroom. So we are also ensuring that the messages from same device ID goes to the same partition. So we preserve the ordering per device. So finally, more partition give us a better fault tolerance and rebalancing the load. Okay. So if a consumer node fail, the partition it was consuming from can easily be reassigned to others. So that we have that resiliency built in the system. So this is kind of a rough calculation. Maybe 24 might be too high, or maybe it be low, maybe it could 40 could be too high, but I'm just trying to give you the message, like if at all you want to arrive at number of partitions, how do you go about actually doing that in a systematic way instead of choosing a random number. Or other could be like you try with some start some partition and see, do some load testing, how throughput is there. Or another option is that you can go for serverless, where you don't have to really worry about all these things. So this will be the end of our first stage, which is ingestion. Then next we'll look at, now the data has landed in the Kafka, but we need to process it. Now we'll look at what are the key design considerations when we want to process this data landing in this Kafka.